Welcome to The Explainer. Today, we're going to talk about a quiet revolution happening in electrical engineering. It's a story about how your phone charger, of all things, is pushing the century-old math that runs our entire power grid to its absolute breaking point, and how a totally new kind of geometry might be the answer. Okay, let's get into it.
Yeah, I know, it sounds a little weird, but it's totally true. Every single time you plug in your phone, your laptop, or even just flip on an LED light, you're actually contributing to this massive growing problem. You see, the modern electronics we all use are creating a really fundamental challenge for the math that our power grid has relied on for over 100 years.
So, what is this problem, exactly? Well, it all comes down to how electricity itself has fundamentally changed. The nice, smooth, clean power our grid was designed for, it's being replaced by something a whole lot messier.
If you could look at electricity 100 years ago, it would have been beautiful. Just these perfect, predictable sine waves. Super simple. But today's grid? Oh man, it's filled with what engineers call nonlinear loads, which is just a fancy way of saying modern electronics. And they create these jagged, distorted, really complex waveforms. Honestly, the difference is like going from a pure, clean musical note to just a chaotic blast of static.
And the culprits, they're literally all around us. In fact, it's the very technology we use to be more efficient. We're talking about LED lights, the power converters inside our TVs and computers, solar inverters, EV chargers, you name it. They all work by chopping up electricity into little bits instead of drawing it smoothly. And it's that chopping action that completely mangles that once clean sine wave.
Now, this distortion isn't just messy, it actively creates something called harmonics. The best way to think about them is as high-frequency noise, like little echoes or vibrations riding on top of the main electrical signal. And these harmonics, they make trying to analyze electrical circuits incredibly difficult with the tools engineers have been using for over a century.
So, let's take a look at that old toolbox. For more than 100 years, electrical engineering has relied on this absolutely brilliant method. But it's a method that's really starting to show its age.
Okay, so the story starts way back in 1807 with Joseph Fourier. He had this amazing insight. Any messy wave, no matter how complicated, can just be broken down into a bunch of simple, clean sine waves added together. Total game changer. Then, fast forward to 1893, and this engineering genius Charles Proteus Steinmetz uses that idea to create something called phasor analysis. This thing was incredible. It turned super complex calculus into much simpler algebra, and for over 100 years it's been the absolute gold standard.
So what is phasor analysis? At its heart, it's a really elegant trick. It uses something from math called complex numbers. Now, don't worry, you can just think of a complex number as a single point on a 2D map. And that one little point can tell you two things at once: how strong the electrical wave is and its timing, or its phase. It's a hugely powerful shortcut for engineers.
And hey, don't just take my word for it. As one user on Reddit put it just brilliantly, this was revolutionary. Instead of having to solve these nightmare differential equations to figure out what a circuit was doing, engineers could suddenly just use basic arithmetic. I mean, it made everything faster, simpler, and way more intuitive. It sounds perfect, right? And for a long time, it was. It was absolutely perfect for the world it was designed for. But today, this powerful, elegant method has one fundamental limitation that's become a massive problem.
And here it is. This is the whole problem right here. Phasor analysis was designed for a world with one single, clean frequency. It is perfect for analyzing a pure sine wave. But our grid today isn't a single sine wave anymore, is it? It's a distorted mess made up of the main frequency plus all of those high-frequency harmonics we talked about.
So to cope with this, engineers have to use this really clunky, fragmented workaround. First, they use Fourier's old trick to break the messy signal down into all of its individual little sine waves. Then, they have to solve the circuit over and over again, one time for every single harmonic. And finally, they have to painstakingly stitch all of those separate answers back together. It's slow, it's inefficient, and you totally lose the big picture of what the circuit is doing as a whole. So, this massive inefficiency has led some researchers to ask a really radical question. Instead of just trying to patch up the old method, what if we could rethink the entire problem from the ground up? And this is where a completely new kind of geometry comes in with a much more elegant solution. And this is the key question, the big what if? What if we could analyze the entire distorted multi-harmonic wave all at once in a single step? What if we didn't have to break it into pieces at all? This new approach asks us to completely change our perspective on the problem. So think of it like this. The old way forces us to imagine each harmonic living on its own separate, flat, two-dimensional sheet of paper. You analyze one sheet, you put it down, you pick up the next sheet, analyze it, put it down. It's a totally fragmented view. The new approach says, forget the stack of paper. What if we could see the entire signal, all of it, as one single, unified geometric object, a single vector living in a multidimensional space?
And the mathematical tool that makes this all possible is called geometric algebra. You can think of it as a serious upgrade to our math toolkit. It basically unifies the ideas of vectors and complex numbers into one super powerful system. So instead of being stuck in 2D, it lets us represent that entire messy waveform with all its harmonics as a single object in a higher dimensional space.
And this new language, this new math, gives us an incredibly powerful new tool, a single operator that can describe how a circuit responds to that entire messy waveform all at once.
And this new tool is called the Rotoflex. Now, for any engineers watching, the simplest way to think about this is like a supercharged version of the old concept of impedance. It's one single mathematical object that describes the circuit's total response, how it changes the strength and the timing of a signal, but it does it across all the harmonics, all at the same time. Okay, so this all sounds amazing in theory, right? But does it actually work? How does this new geometric approach really stack up against the classic, tried-and-true method that's been used forever?
Well, the researchers ran the numbers on some test circuits, and the results, they speak for themselves. It is a perfect match. For every single harmonic they tested, the new geometric algebra method produced the exact same magnitude and phase as the old classical method. This proves, without a doubt, that the new framework is numerically identical and completely accurate.
But here's the thing, being just as accurate isn't the whole story. This new framework is better. By solving the entire problem in one single shot, it's way faster and more efficient, which could lead to much better design tools. And this part is cool. By revealing the hidden geometry of the problem, it actually gives engineers a deeper, more intuitive understanding of how their circuits really work.
The researchers themselves conclude that this isn't just a different way of doing the same old thing. No, they argue that geometric algebra is a true evolution, that it's a conceptually and computationally superior successor to the method that has defined electrical engineering for over a century.
And that leaves us with a final, kind of provocative thought. This work shows the incredible power of finding the right mathematical language, the right geometry to describe a complex problem. And it really makes you wonder, doesn't it? What other complicated systems out there, in physics, in finance, even in biology, are just waiting for us to discover the new geometry that will suddenly make them simple?